Bi 170? No, but what about Bi 101? They use it maybe. Anyway, okay. They use those terms. I wish I could go back and take biology classes again, just sit there and laugh at the different terminology, even the same thing. Again, it's just a different concept. So exergonic is what the biologists use to describe energy being released, and endergonic versus endothermic means energy being consumed. So some reactions require energy in order for them to happen, and they actually feel cold to the touch. They absorb heat from their surroundings. So that's where the term endothermic comes from. If you have a delta H with a negative sign, okay, it means that energy is released. It means it's exothermic. Okay, this example with, actually both of these examples were exothermic processes. Right? The energy is released. They feel hot to the touch. I want to apologize for my bulleting here. This should just be like a bullet sign. It's not a negative sign. So just maybe just make a little circle there. Little circle there. Yeah, those are not negative signs, they're just bullets. That's the default for PowerPoint. Anyway. But sometimes delta H is positive, and it feels cold to the touch. Can anyone think of a reaction that you might do in your daily life that might feel cold to the touch? How many of you have injured yourself during a sporting event or doing sports? How many of you have used the ice pack before? Yeah, all the time, right? So what that is it's the solvation of ammonium nitrate, and you break that barrier between water and the salt, and it dissolves into the water, and it actually is an endothermic reaction, and it feels cold to the touch. And you use that, of course, to put on your sore knee that you just hurt, and helps kind of get the swelling down. So that's an example of an endothermic reaction that we use in our daily lives. Right? Exothermic is a little easier to say. Yeah, okay, we barbecue, exothermic. We exist, exothermic, right? We have a normal body temperature of 98.6 degrees Fahrenheit. That's naturally warmer than the room temperature, usually, right? The reason why is because we're producing some energy as we exist, right? It's because it's when we see IR radiation coming from us with IR lenses, right? We can see that glow if we're looking at people through a IR lens. We drive our cars, we burn fuel in our cars, exothermic. Right? So we're using exothermic reactions all the time, endothermic not as much, but we still do. So this gets me to thermochemical equations, and you've seen this in Chem 107 too, but they maybe didn't call them thermochemical equations. So when you have a reaction, okay, in this case, this is propane reacting to oxygen, produces carbon dioxide and water, and it has an enthalpy change associated with it. If it's negative, what does that mean? It means it's exothermic, it releases heat. So that makes sense, right? You're barbecuing. Usually people barbecue with a propane tank, right? You burn that propane, it releases lots of heat. And that heat goes where? This heat goes where? Into the surroundings. What is the surroundings? Your steak, your hot dogs, your burgers, okay? Your hand, hopefully not your hand, okay? But the food you want to eat, right? So again, I'm trying to always get you to think system surroundings, first law, okay? This is the system, the surroundings, this is delta H of the system. The surroundings would be what? Positive 2000 or 2044, right? What thermochemical equations do, and this is an example of a thermochemical equation. Okay, a thermochemical equation is just a chemical reaction with an enthalpy value assigned to it to the side. That's all it is. But what a thermochemical equation does is it relates an amount of energy to how much we burn. So if I doubled the moles of propane, which would make me have to double the moles of oxygen, which would double the moles of carbon dioxide and water coming out, what do you think this value would become? It'd be double as well, right? It would release double the energy. So what thermochemical equations help us do is they help us assign energy to the amount of product produced or the amount of reactant consumed. And we can establish mole ratios of energy to moles with this. Okay, so for example, for propane, we can say, okay, delta H reaction is going to be negative 2044 per 1 mole for propane because the coefficient is only 1 mole in front of it. But for oxygen, it'd be negative 2044 per 5 moles. Okay, so depending on what molar amount we're working with, it'll change the ratio. Okay. So those are thermochemical equations. So let's do this problem. How much heat in kilojoules is given off from the combustion of 13 kilograms of propane? How much heat can we get from that? So look at thermochemical equations as an energy to an amount ratio. It's like a constant ratio. But then we have this different amount that we need to burn. So we have 13.2 kilograms of propane. We're going to multiply it by something. All right, how do we get to, what is it asking us for? How much heat in kilojoules do we have? All right, so how much energy? Okay. In other words, if 1 mole of C3H8 gives 2044, then how much energy does the 13.2 kilograms give us? That's another way of stating this question. So one thing that might be helpful is if we convert kilograms into moles, and then go from there. So the molar mass of propane is what? Actually, let's convert it to grams first. How do we get from kilograms to grams? Is it 1,000 over 1 or 1 over 1,000? Yeah, 1,000 over 1. So we have 10 to the third grams for every 1 kilogram, or 10 to the 0 kilograms. Okay, now we get for every 1 mole of C3H8, we get 44.11 grams for the molar mass. So what does that give us in terms of moles of propane? Right, so you got 13.2 times 1,000 divided by 44.11. And that gives us 299.25 moles of propane. So again, 1 mole gives us this much energy. How much energy does this many moles give us? So if you are still doing high school math, you'll know that you can set up a ratio of 1 mole over X equals 299.25 moles over X equals 1 mole over that. And you can solve. But I don't like doing that because that's just high school. So let's just do the conversion. So 299.25 moles of propane. And we know that we have 2044 kilojoules for every 1 mole of propane. All right, so that's going to give us a pretty big number. write out the number though. So it gives us 611, it's a big number, 670 kilojoules. So you're right, so this is a negative sign here, right? All right. How many sig figs do we round this to?
3.
It'll be 3 because 13.2 kilograms. So I'm going to go ahead and rewrite this as 6.12 times 10 to the 5th kilojoules. And it's going to be negative. So delta H is equal to negative 6.12. The thing is, the question's asking us how much heat. So when it asks you how much instead of the change of, we don't care about the negative sign. So we just say, we can say how much, we can say heat released is going to be equal to 6.12 to the 5th. But again, if you just gave me a negative sign, that's fine. I'll take that. Okay. But in your mastering chemistry homework, it might be a little sensitive to that, just FYI. So it asks for how much heat is released. Just take the negative out. Okay. Versus it asks you for the change in energy, keep the negative in there. Where does this 2044 come from? How did they get that? How did they measure enthalpy in general? Enthalpy, calorimetry, right? So this is how they got it. This is just using it at that point. So one thing that sometimes happens, if you want to combine concepts, so you want to get, if you really want to know this stuff, and I like combining concepts sometimes, okay, you might get a calorimetry problem that forces you to calculate delta H this way, and then you use it to plug it into this problem right here, and go from there. So trying to connect ideas here. They all look like different problems. You're like, oh yeah, he gave us a thermochemical equation problem. He gave us a coffee cup problem. He gave us a bomb problem. He gave us last time a thermochemical equilibrium problem. But to relate them all, okay, just understand delta H calculated from calorimetry can be used to figure out what the enthalpy is of various reactions. And so in Chem 107, they just told you, here's the equation, here's delta H, use it. In this class, we're also telling you, well, here's where it comes from, calorimetry. All right, that's the next step. So just to try and tie some ideas together, that's what I'm trying to do. All right. All right. Any questions? Not right now, probably, but many later, many to come. All right. So it looks like it's time for us to head upstairs, but we'll leave it at that.